Get our slide set up for the current slide, and we are ready to go. As far as, I don't know of any major announcements to talk about, so let's get right on to how the class, where we are, what we're doing now. We started last time, just barely got started in chapter 16, but we did finish last time chapter 15 and did the lab for 15. Now I know a couple people weren't here, right here for last time. A few of you weren't here last time? Right, yeah, okay. So here's the lab. Anyone else? Now I think you can listen on the YouTube video and probably get most of it. Anything you can't get, you probably can get with someone else. Now, did you get a lab? I know you had to leave early.
You gave me one, and that's what I was about to ask you about. There are 3 questions that toward the end of the video you can't understand. It just sounds really far away and muffled. So I really can't hear what you're saying. Okay.
So those, if you can get with someone, did all of you turn it in that were here last time? I'm afraid you probably did, didn't you?
6, 7, and 8 is the ones that you gave.
6, 7, and 8. Okay. Now, if my memory's right, I was sitting right here, so I don't know why the sound may just not have been doing well.
I played it 2 or 3 times.
Okay. Let me see if anyone who was here last time. Yes, I think Kayla was here. Did she leave early? I didn't mark her if she wasn't. So there are some floating around out there. What we'll have to do, though, is we can't really afford to take too much of today's class time. What I can try to do is tomorrow afternoon after 2 o'clock. Is that a decent time for anybody? Okay. Why don't you come in tomorrow afternoon after 2 or after 1:40? I'll be in this room. We'll just have taught a Calculus 2 class. I'll be shutting down, so it takes a while to get everything done. Why don't you come on in and we'll go over those last 3 questions.
Thank you.
Okay? So anyone else who was not here last time, talking to that, I don't know why, because I know the Rip Van Winkle one, I think I was sitting right here pretty much for it, because I was having to draw things on the screen, and you could see the things get drawn, but you couldn't hear what I was saying. And I had to be sitting right here on the screen to do that. Yeah. And that was bizarre, because if you see me writing, I have to be right here on the screen writing. So evidently the microphone must not have been working well. Now let me know if it's going out. I need to know that, and either get a new computer or get a new mic put in, or an external mic or something, because that's sort of concerning, because I couldn't have been writing on the screen without sitting right in front of it. So that's I'm glad you told me. Listen up for the next ones, okay? Anyone who's listening at home, you'll let me know that too. Okay, so we're going to continue in chapter 16 today. Now we've got an hour and 50 minutes of class, and then technically an hour and a half of lab. Okay, don't think we're going to have time for a lab today, so we'll just go all the way through this chapter. We got quite a bit to go, so I think our hour and 50 minutes will certainly be filled with that, and we'll probably move on into lab time. Now, we'll probably finish the chapter, I'm guessing now, finish the chapter before 3 o'clock, okay? So what we'll do then is continue and start in chapter 17, just sort of get started in it. If we were to finish the chapter, which I don't think is going to happen, we would have to, let's see, 30 minutes. by 1 o'clock, which isn't going to happen, I don't think. If we were to finish by 1, we would have time to do the lab from 1 to 3 and then the test from 3 to 3:30. Don't think that's going to happen, especially since it's already almost 12:10 or so. So I think we will do as much as we can, if not all of Chapter 16. If we have any time left over before 3 o'clock, we'll start on Chapter 17. And then that means next time, that'll be Thursday, we'll have the lab for Chapter 16, and then probably the test in 16. If we finish Chapter 16 today, the test will also be on Thursday, the last 30 minutes again. The lab will be the 2 hours previous to that, and the time spent on Chapter 17 will be, whatever we have, the 1 hour before that. 1 hour before that. So that makes sense? Okay. So let's get going on this. Any questions from anything we've done so far? And remember, on every test, today's test, every test, you can have a formula and equation sheet with you during the test. Okay? Anything you want to write down on a piece of paper. All right. We were just beginning to talk about motions of the earth. Okay? And some of these motions, the first one now, the text titles and the PowerPoint titles aren't quite the same, but it means the same. And the book is The Orbit, which this is calling the revolution. Okay? So what do we mean by that? That's the Earth's movement around the sun. Now, we've talked about that several times in the last chapter and this chapter, probably the previous chapter. Okay? The orbit defines the plane of the ecliptic. When we go around the sun, we go around and we are always on the same plane. We're not doing this kind of stuff. We're not, changing or anything. We're on one plane. Okay? Is it Cassidy?
Yes.
Yeah, okay. And there's Justin. Okay. Now, let me just quickly, for the two who just came in, say again what today's going to look like. I have a feeling we will be in Chapter 16 most of the day today. Now, when 3 o'clock comes, we're going to stop wherever we are, and that's where the test for Chapter 15 will be the last 30 minutes a day. And you can't have formula and equation sheet, anything you want to write on a piece of paper. Also, while I'm thinking of it, some of you were not here last time, right, and so you did not get the last lab, right? Okay. Here's the lab. Now, I've heard from one of the students who was not here that everything except the last 3 questions showed up okay or sounded okay on the YouTube video, but I can't figure out why the last 3 questions did, because I was drawing on my screen at the same time, so I was just as close to the microphone. So what we've decided is tomorrow, sometime around 1:40, 1:45, 2 o'clock, sometime in there, come to this classroom and we'll go through those last 3 questions on the lab, if you want to get that. Or get with someone who was in the lab and they can remember how that worked. I think just about everybody turned in their labs. One person may not have, but she's not here right now. Okay. And the last 30 minutes today we have the test on Chapter 15, and you can have formula and equation sheet for that. If we finish Chapter 16 today, which I think is a pretty good shot we will, then on Thursday, we'll both have the test on Chapter 16 and the lab on Chapter 16. So that's 30 minutes from the end, 2 hours before that, so we'll only have an hour to be on Chapter 17. We may get started in 17 today, and we'll pick up and just do an hour worth there. Now, if we don't finish Chapter 16 today, which I think we should, but if we don't, then we won't have the test next time. We will have the lab, but not the test. I always like to have finished the chapter the day before the test, so you don't have new material in the same day as the test. All right, So we were talking about revolution of the Earth around the sun. That goes in a sort of a flat plane, okay? And basically just about all of the planets are in the same plane. Some of them tilt a little bit reference to the others, but not much. Now the dwarf planets, way outside. That's why Pluto is now a dwarf planet, one of the reasons. The comets, they come and go however they want to. Remember the comets mostly come from the Kuiper belt, which is a lot thicker plane than the planetary belt. That's where Pluto is in that. Or from the Oort cloud, which can be from any place, because that's the whole cloud around the sun. And I mean, it goes out a long, long ways. Okay? But for our revolution around the sun, that defines the plane of the ecliptic. Okay? That means, we're tilted, so the ecliptic is going to be like this, where we're tilted like that. Okay? So the ecliptic is always in line with the sun, where our tilt, our equator, nothing else is, just the ecliptic. So the ecliptic is the apparent path that the sun goes through the heavens. Okay? So picture this. Let's start. I had the globe out here. You tilt it here. This would be close to, this would be probably July or August right here. Oh, I can't get right over there. Okay? And the sun's there. The stars are back there. Now, in the daytime, you can't see those stars. Those are the stars opposite the sun. When we turn, those are the stars. But when we move over here, we see a different set of stars. Move over here, we see a different set of stars. Move over here, you see now we're looking at completely different sky than we saw at the opposite time. That was summer, this will be winter. Completely different set of stars. Okay? Now, the sun turn in and out, so that's why the apparent path of the sun through the heavens is seen from the earth. Okay? Now, we are in an elliptical orbit, not quite a circular orbit. Okay? This is Caleb. Okay. Now, I can't remember. Were you here for the lab?
Yeah, but I have to turn it in.
Yeah, I know you didn't turn it in. Now, here's another option, folks. There were 3 people so far were not here last time that were here this time. Everybody except you turned in their lab. Do y'all want to get with, would you mind if they got with you? They said they could hear all but the last 3 questions. For some reason, the microphone wasn't picking up well. And go over that with them, because I've graded everybody else's. Or we can, the alternative would be...
You mean on the YouTube video?
Say again?
You mean on the YouTube video?
Yeah, on the YouTube video, they said they could not hear the last 3 questions. They were muffled. Okay? The first part they could.
Okay.
Okay. So you don't have to do this if you don't want to, but if you want to share that with them, say after class or sometime, or if not, I'll just go over that again tomorrow afternoon around 2 or so.
That's fine. It doesn't matter.
Okay. Y'all want to get with Kayla, or would you rather get with me tomorrow afternoon? The 3 of you are here. Huh? I'm sorry, I can't hear.
They said they'll get it from me.
Okay. How about you?
Yeah,
Okay?
that's fine.
All right. Otherwise, I'll be here at 2 tomorrow afternoon. And if I'm not here, check my office. Okay. So, we are not quite in a circular orbit. We're in an elliptical orbit. What that means, there's sometimes during our orbit, we're further from the sun, sometimes we're closer to the sun, and we're always, it's not quite circular. A circle, say, is like this, and an ellipse would be a little more egg-shaped. Kind of. Not quite egg-shaped, close. And believe it or not, the time we're closest to the sun is in January. The time we're farthest from the sun is in July. Okay? Now that sounds like it doesn't make sense, does it? Okay? But it's not much difference. Okay? The Earth receives only about 6% more solar energy in January than it does in July. That's the whole Earth. What makes a difference for us, that in July, and this is about where we'll be in July, even though we're farther from the sun, we're tilted toward the sun. And more direct radiation from the sun gets through our atmosphere to us than in January, when we're tilted away from the sun. And even when we spin, even though we're closer to the sun, the difference is that tilt carries the sun's radiation more through more of the atmosphere and for fewer hours, so we wind up not as warm. Okay? Now, it says 2.5 million kilometers closer in January. Now that sounds like a lot, doesn't it? But when you consider that's about 1.6 million miles closer in January, 1.6 million miles farther in July. But when you consider we're 93 million miles, what is 1.6? You know, that's barely, it's not even 2% closer. It's between 1 and 2% closer. Not very much at all. Okay? The important thing is that the amount of atmosphere the sun's rays go through. Okay? But, picture this. What if you lived in the southern hemisphere? In the southern hemisphere,
you'll see more.
Yes, you're closer to the sun and tilted toward the sun in January, and you're further from the sun and tilted away from the sun in July. And that's your wintertime. That is your coldest part of the year. Australia. I've often wondered, I never have looked in to see if there's a difference, if they have greater variation between their summer and winter temperatures than we do. My guess would be yes, but I don't know that for a fact. The thing that moderates someplace like Australia is they're surrounded by water. And water acts as a moderator, okay, a buffer, and it keeps you warmer. That's why at the beach, if you're going to the beach in the wintertime, it's usually a little bit warmer. It's still cold, but not as cold as it is inland. You go to the beach in the summertime, and I swear, driving from here to the beach, further south you go, the temperature gets warmer and warmer generally. Boy, Montgomery's hot. And then you get even closer to the beach, it's hot. When you get right on the beach, it feels a little bit cooler. I mean, it's hot on the beach for sure, but a little bit cooler because the water is a buffer, you might say. All right, Lauren's here. Okay. So, that's all parts of our revolution around the sun. Okay? This picture illustrates it, exaggerates it big time, but illustrates it. Around June the 21st, we're as far from the sun as we're going to get. Well, more like July, but you're getting close to that. Direct sunlight lands right on, let me go and get my globe here. Okay? So how much is our tilt? How much tilt do we have with the Earth axis? 23.5 degrees. Perfect. 23.5 degrees. So therefore, in the dead, you saw how summer solstice, the sun is directly over 23.5 degrees north. Because our equator is actually below, that's where the sun is. Directly overhead, 23.5 degrees north. That means Havana, Cuba, right overhead then, shortly thereafter. Mexico, north of Mexico City, is directly in line with that. Hawaii, the northernmost island, one up just below that. And what do we call that line? 23.5 degrees north? Second? Almost said something. That sounded close. It's the Tropic of Cancer. One in the southern hemisphere, degrees south. Okay? So, dead heat of summer, the sun is directly overhead here. That means here in Alabama, it's not far from being directly overhead. It's only about 11 degrees off. So we get direct radiation, almost direct radiation from the sun. Okay? Now, and that's why all the northern hemisphere is in summertime. Even though we're almost as far from the sun as we're going to get, that difference is very small. The tilt is very, very, very major. Now, what about March 23rd, 21st or so?
And when everything kind of.
Yeah, the sun's directly over the equator there. Okay? Directly over the equator. So everybody is 12 and 12. 12 hours of daylight, 12 hours of dark, because everybody gets equal amount of sun. Okay? And you get over here to December 21st, when we're as close to the sun as we ever going to get as the Earth, the tilt has us so that we're facing the other way. So even when Birmingham at noon on summer, noon in wintertime in December 21st, directly overhead the Tropic of Capricorn. And look how far we are from there. So the rays are going through a lot more atmosphere, losing a lot more energy, and with the sun's not up as long. Okay, so several reasons we're colder in the wintertime. Okay? Come over here to September the 21st or so. Now the sun's directly overhead the equator. So the sun's directly overhead, always something between 23.5 degrees north to 23.5 degrees south. Between the tropics, Tropic of Cancer in the north, Tropic of Capricorn in the south. That's the only band that ever has the sun directly overhead. Tropic of Cancer once a year, around June 21st. Tropic of Capricorn once a year, around December 21st. Everywhere else, twice a year, shortly before, shortly thereafter, some on the equator, directly overhead, March and September. Does that make sense? And that's why the tropics are typically warmer, because they always, at some time of the year, the sun's directly overhead, and never is it very far from being directly overhead. Okay, so that's what this describes. Even though we're further from the sun, we're tilted toward the sun, more direct radiation coming on the northern hemisphere. In fact, inside the Arctic Circle, the sun never sets on June 21st or 2nd. Okay? The further north you have, the more days it never sets. Right on the Arctic Circle, it never sets that one day, June 21st or 22nd. And the reason for that is here. I think we did this one time before. Here's the Arctic Circle. How many degrees away from the North Pole? How many degrees would the Arctic Circle be away from the North Pole? 23.5 degrees. So that would be 90 minus 23.5 would be 66.5. Is that right? I think so. 66.5 degrees from the North Pole. So let's see if that's right. Figure gives it right. So, yeah, here we go. There's 60 degrees, that's 66.5, and anywhere on up to 90. And right here, if you look, here's the sun. Does the North Pole ever get out of your sight? It's always there. The sun's always up. Not very high, but it's up all day long, 24 hours. Now, only on the Arctic Circle, that's the only day it's going to be. Anytime later, the sun will go down just a few minutes and go back up. But up here, it's still up all the time until finally it continues until it has something like that darkness. Okay. So that identifies the Tropic of Cancer right there, where the sun's directly overhead on summer solstice. On the equinox, both the vernal and autumnal equinoxes, directly over the equator both times. On December 21st, 22nd, 23rd, sometime around in there, the sun's directly overhead, the tropics of Capricorn in the southern hemisphere, 23.5 degrees south, and that's where it's directly. So all the trip around here, the sun's directly overhead, only between 23.5 degrees north, only one day a year there, twice a year in where between there and tropical Capricorn, well, tropical Capricorn directly overhead on the winter solstice, whenever that is, directly over the equator. Okay, so like I said, this is summer solstice when the sun seems to stand still, and you see the part of the half of the earth is toward the sun, or is in daylight, and as the earth's spinning around the axis, this is daylight 24 hours anywhere inside the Arctic Circle. Which means inside the Antarctic Circle is what? Hours of night. The sun never rises inside the Antarctic Circle. Okay? That's the Antarctic Circle down here. Just about all of Antarctica is in that. There's a little peninsula that comes up out of here. Just the tip of a bulb there and there. A few places there. All the rest of us inside the Antarctic Circle. Inside the Arctic Circle up here, you have about the upper third of Alaska, the very upper part of Canada, just about all of Greenland, I'd say 2/3 of Greenland. Iceland is just below the Arctic Circle, okay? The upper fraction of Norway, Sweden, Finland are all above the Arctic Circle. And then a huge part of, not a huge part, but a significant part of Russia is above the Arctic Circle. Not the majority, but a significant part. What they usually refer to as Siberia, mostly, it's really close to the Arctic Circle. And I think I mentioned the last one. So that's the part that in the summer solstice, everything in there is 24 hours of daylight. In the winter solstice, everything in the Arctic Circle is 24 hours of darkness. But in the southern hemisphere, the Antarctic Circle, winter solstice, our winter solstice, the summer solstice, is completely daylight. And our summer solstice, there's winter solstice, 24 hours of darkness there. It's only on the Arctic Circle you have that, only that one day. You go in, there's a few more days a year that you'll get 24 hours of darkness. So in Alaska, upper regions of Alaska, when they have that, they say that up there there's a lot of depression. That's in the U.S. People just get stir crazy. They don't get enough sunlight because we really do need some sun. Okay, we do as animals. We go around the sun like this. Now, of course, the sun is ill represented here. The Earth looks bigger than the sun. Nowhere close. But if they show sun full scale, we would be just a little bitty dot. It would be hard to see this. So this is not in scale. And this distance is way too great. That's way too small. They're emphasizing it. There's only 2.5 million miles out of 95 million. So I said it wrong. A little less than 3%. Okay, I said 2%. A little less than 3% difference, in that. So in reality, slide this whole thing about to here. Okay, that would be more representative. Let's see here, a little bit further here, and a little bit closer there. It's just not exactly circular. Any question? Okay. Now let's go to the next movement of the sun, and that is the rotation. And I wish they still showed this one. This is probably your better shot that I think they showed before of the ecliptic is the blue circle. The equator is this one, so therefore it shows maximum deviation from the ecliptic in summer solstice and winter solstice, and right on the money spring equinox and autumnal equinox, the 2 circles coincide. That's why we started our star gauge guide always at 3 equinox, so that's the same. Okay. All right, now this is a question that you should be able to answer based on the labs that we've done. What is the latitude of an observer who measures the sun's altitude of 38.5 degrees above the southern horizon at noon on the summer solstice? What would be his latitude? He's measuring the sun's altitude to be 38.5 above the southern horizon at noon on the summer solstice. So what is his, what is the latitude of that observer? Remember that? That was the first question on the first lab. Second? What did you say? Okay, it's the difference of that in 90 degrees. So you subtract 38.5 from 90 degrees.
52.5.
Wait, that's not quite right. Okay. Okay. It's a combination of several things. I thought it was going to be a little easier than that. But it goes back to our, let me get my pen set up. Here we go. Remember how we did this? If the sun is 38.5 above the southern horizon. So here it is. This is 38.5 degrees above the southern horizon. This is the sun on summer solstice. Okay? Now, that's what you know. Where is the celestial equator on summer solstice? Where is the celestial equator on summer solstice? (23.5 degrees) let's see how the best way to say this. The sun is 23.5 degrees above that. So here would be 23.5 degrees. This is celestial equator. Okay? 23 degrees, 30 minutes. Okay? The sun would be that far north of the celestial equator. So, if that's the celestial equator here, the what is this angle here? So that's the difference between it. And this is 38.5, that's 38.5. I should have used the same notation. Let me change that slightly. Make it 0.5. Oh, I lost my celestial sphere. Oh no. Okay. Okay. There's the celestial sphere. This is 23.5 degrees. This is 38.5 degrees. This is 23.5 degrees. 0.5. That way it's easier to subtract. What's the difference between these two? 15. Okay. And subtract that from 90 because the North Pole is 90 degrees from the celestial equator. So this is 15 down here. Subtract that from 90, and what do you get? 75. So this would be 75 degrees over here, and that would be the altitude, the latitude that you would be 75 degrees north. Okay. All right. Then the next question, similar to it, what is the latitude of an observer who measures the sun's altitude of 40 degrees above the northern horizon at noon on the summer solstice? Okay? Well, if it's 40 degrees above the northern horizon, that means they're in the southern hemisphere. And you can go through the same type maneuvering. You just have to flip it around, and you'll come out with 26.5 degrees south. So that's not very far down, just below the Tropic of Capricorn. By the way, I don't guess I realize this as much. At least half of Australia, awfully close to half of Australia, is in the tropics. I knew that the northern part here was tropical. I didn't know that much of it was. My wife went to Brisbane, which is just a little bit south of the tropic, and she said it was very, very pleasant there. She had to take my music set. I was just going to say Sydney is not too much further from south of the equator than we are. Birmingham from north of the equator, so you get a bit of all four there. So it would have to be down here on Tasmania, or Tasmania or somewhere, where you really, or New Zealand, you see a great difference in what we want to think about temperature-wise. All right, that's probably more than you wanted to know about that. So let me erase that ink. And now we start talking about the rotation. Now, what can you tell me about the rotation axis? That's what? 23.5 degrees, okay, incline. Okay? Now that rotation axis, with the fact of the tilt, that determines our seasons, which we've already talked about. Determined by the orientation of the axis. The winter solstice marks the beginning of winter, okay, which is around December 21st. Does that mean it's the coldest day of the year?
No.
No, not necessarily. The main reason for that is the water. The Earth is covered with about 70% water. Okay, so that moderates our temperatures a lot. So that makes the coldest day a little bit later because you have to let the water cool down. Okay, but anyway, that is that's when winter begins, and at winter solstice and goes to the equinox. That's when spring begins. Okay, and then spring goes from equinox until summer solstice, and that's where summer begins. So right now it feels like summer outside, but we're awfully close to the summer solstice, but we're still in spring until we get to the summer solstice. Then summer begins at summer solstice and goes until the autumnal equinox, September 21st or so. That's when autumn begins, and it goes till December 21st, which is when winter starts again, so winter solstice. Now, our celestial equator, remember, is tilted according to what our latitude is, okay, as the line of the celestial sphere above the Earth's equator, okay? So if we're like this, then the celestial equator is like this too. You just extend that like that, okay? Now, why bring the celestial equator in? Same reason we were doing, oh, here's that picture I was talking about. Here is this is the ecliptic. The blue line is the ecliptic. The pink line is the celestial equator. See, it's parallel to the Earth's equator here. The tilt is 23.5 degrees. The sun is above the equator by 23.5 degrees on the summer solstice, below on the winter solstice. That's why the northern hemisphere has summer here. Southern hemisphere has winter then here, and then on winter solstice we are in winter, they're in summer. That's the ecliptic. Equinox is when equal day, equal night. That's when the ecliptic crosses the equator, celestial equator, and that's twice a year. Once in spring, once in fall, that determines our equinox. And that determines the end of summer, end of winter, beginning of spring, beginning of fall. Okay. Now, how do we know the Earth rotates? Maybe the ancients were right, and the sun really is moving around the Earth. It feels like we're still. I don't feel us moving any. I don't get slung out, you know. How do we know the Earth rotates? Is there any evidence besides this model that we have? Well, several. Starting with Galileo. Galileo improved the first telescope. Somewhere up in northern England, northern Europe, the guy had developed the first telescope, but it wasn't a very strong telescope. Galileo heard about it, read about it, started messing around with it. He improved it big time. Then he started looking at the heavens. And that big bright thing that everybody thought was a strange acting star turned out to be a planet. That was Jupiter. And when he looked through his telescope, guess what? He saw that Jupiter spun. He couldn't actually see it spinning, but he knew that night after night the great red spot was moving. Okay? Or even early in the night to late in the night, he could tell it was moving. So obviously Jupiter spins. Now don't do this, but if you were to take pictures of the sun, don't look at the sun, don't ever look directly at the sun, you can burn your retina and develop loss of vision, permanent loss of vision, or partial loss of vision. But you won't get it back because that's too bright. Okay? But if you take pictures of the sun and look at them at different times, you see the sun is spinning. So guess what? If the other bodies in our atmosphere, our solar system are spinning, why wouldn't the Earth be spinning? So that's one piece of evidence. Other bodies we can tell are spinning, especially Jupiter and the sun. Another one. I've asked this several times. Have you ever been to McLean Science Center? Okay, over in one corner is this huge pendulum, or it used to be. It went like that. It's called the Foucault pendulum. The first one was done in France. The guy named Foucault, I think is how you pronounce that, did it. And if you start these spinning, just going back and forth, and if you look at that 3 hours later, it's like this. It's not spinning. It's not spinning. It's not going back and forth in the same line. It only moves a little bit, so you never notice until you wait several hours, and you'll find out it's going in a different direction. It's moving slightly all the time. That's because the pendulum oscillates in a fixed direction. Okay? The orientation changes as the Earth rotates. That's why I said allow it 6 hours and you'll see about a 90-degree change in 6 hours. Okay? Pretty obvious. And here's the third evidence. This was discovered by, I think, an Italian guy named Coriolis. It's called the Coriolis effect. If you were to drop something from way up there, the deflection of the path as the Earth rotates beneath the object's falling. If you were to map that, say you dropped it directly over where you want to drop something. Pick a town, pick a city, someplace you want to hit, okay? Name one. Okay. Birmingham, Alabama? I want to pick a city, Birmingham. So if you're way up there, and you dropped it when you were directly over Birmingham, Alabama, by the time it hits the Earth, it's going to hit us. Okay? Or somewhere else, because the Earth is spinning underneath. That's that apparent deflection of the path as Earth rotates beneath moving objects. And those folks who are bombardiers, in the big wars and things we've had, those from the jets that drop them from way up there, they have to account for the spin of the Earth. Otherwise, they're not going to hit the target. They may hit some places they shouldn't hit. And this is an example of why the Foucault pendulum works. if you can imagine a spinning stool, okay, go to one of the labs here, the stool spin. Put a pendulum on a stand like this and start it moving like this, and then spin the stool and you'll see it move like this. Well, the Foucault pendulum does exactly that, and yet it's not on a moving stool, it's on a moving globe, the Earth. So this will illustrate why the arc changes direction. So yes, we know for certain the Earth does rotate. Okay. The Earth does something else, and this is a very slow motion. That's the precession. It's an excruciatingly slow wobble of the Earth's rotation axis. Right now we're at 23.5 degrees, our axis, right? Now part of this, remember the Earth is fatter in the equator and a little thinner at the poles. And because of that, then you have the moon out there pulling on us, the sun over there pulling on us. It pulls more on our gut than it does in the head, okay? And what it does is makes our axis wobble a little bit. It takes 26,000 years for one wobble to happen, okay? So that's really, really, really slow. If and when we do get to the planetarium, and let me talk about that for just a minute. After we do the lab on chapter 16, which will probably be, almost definitely will be Thursday, I'll probably tomorrow afternoon, I've got some time in the office tomorrow afternoon, I'll probably try to get in touch with the guy at the planetarium to see if there's any time that he can take us on a Tuesday or Thursday afternoon between 12 and 3:30. Okay? And frankly, that's all the time I've got. Now, someone was asking, I think early in the term, if we would have a vehicle. If he can't take us until close to 3:30, I cannot drive the vehicle because I've got to be at the Birmingham campus at 4. So he's either got to take us closer to the 12 o'clock time to give us time to get back here and me to get there, or else I can't drive the van. Okay? So what we'll have to do then is see if somebody else, one of the other instructors who would like to go to the planetarium, would drive the van for us. Okay? Because I've got to go late in the day, I've got to be there. So we'll see how that works. So is there, if I can get Tuesday of next week as a day, would that be okay with y'all? To go to the planetarium? Okay, that'll be the earliest that we'll be ready for it. It may not be that it'll fit his schedule. So I'll call him tomorrow and see if the closest Tuesday or Thursday, the soonest Tuesday or Thursday, day after tomorrow, I'll see when he can do it. Do you have a preference on the time? Would you rather it be the early part or the later part? Early, that's what I was thinking too. So, because that way I'll be able to drive the van, get back here, and get to Birmingham on time. Okay, so we'll try to go for early, but we'll have to go whenever you can do it. Yes. What's that? No, it does not cost to park, especially in the summertime. The parking can be a problem in other times of year, but not for cost. It's just finding a close parking place. There's always going to be one up the hill from there, and it's not a far walk, but sometimes you have to drive around to find it. In the summertime, plenty of parking. Just like us, the enrollment isn't as great in the summer as it is in fall. It does not cost. You don't need a pass. You just get there. Okay, so 26,000 years for one precession. When we're at the planetarium, this is what made it pop in my head, he'll point out to you on the planetarium ceiling, that's where the stars are projected. There's the North Star. But at one time, it was Vega, which is over here, was our North Star, because the Earth is precessed. And I think the next slide will show that. It changes the direction of the rotation axis on the celestial sphere. Polaris was not always the North Star. The position of the equinoxes has also changed. Because you see, when the axis changes, our celestial equators change. When the celestial equator changes, you go through different zodiacal signs. Okay, so that will change as well, and has changed. Now here is the representation of this. This is greatly exaggerated, but when you spin a top, because the top is not uniformly positioned, a little bit of perturbation, it's going to sort of wobble like that. Now the Earth does it, but extremely slowly, 26,000 years before it makes one precession. Okay? And this is what it means. At one time in the past, and sometime in the future, like 14,000, okay, we're at 20,000, 2,000 now, 2018. So at 2,000, and another less than 12,000 years, Vega will be our North Star, not Polaris. Okay, that's where we are today, but the farthest out will be that, which means about 12,000 years ago, Vega was our North Star then too. So in between, there may be times we don't have a North Star, or there may be some other minor little star there. Vega's a pretty bright star, so that would be. But guess what? I'm not going to be around this here. Okay, long gone. Okay. In fact, all of us will be. Okay. Now. Okay. Let me keep up with where we are. That's rotation. That's precession. And there is a picture in the book of Foucault. And by the way, that could be a potential paper topic if someone hasn't chosen one. Who was Foucault? How did he deal with that? Or who was Coriolis? How did he come up with his thing? That's 2 or 3, 4 different paper topics there. Now we move to place and time. This is 16.3. Okay? Now these are all things that are determined or analyzed or placed by the spin of the Earth. The Earth's periodic motions provide a basis for determining place and time. Now, time kind of makes sense because time of day, time of year, those motions do that. It sort of doesn't make a lot of sense. How does that determine our place, you know? Well, it's our place relative to changes of that. For instance, how far north or south we are from the equator, how far east or west we are from the prime meridian. That's what it means by that. The rotation provides an axis of rotation useful in determining locations on the globe. So you might think that we came up with the globe first and then talked about the other. Actually, probably our concept of the globe came from the observations we were making otherwise. Okay? The rotation and revolution determine cycles which can be used for time standards. And of course, that's our days from the rotation, years from the revolution. Okay? And then we break those into bigger and smaller units. Okay, so let's identify a place. Now, if we were living on a flat Earth, and some people still think we are, you could do it just like a page of the book. How far from the seam toward the top, from the bottom to the top of the book, and how far right or left you are from the center of the book. That would locate your position exactly. But we don't live on a flat Earth, okay? We live on a sphere, and that's a lot harder to tell, okay? This would be the intersection of two lines. The vertical line, how far from either edge or from the center we are, and the horizontal line, how far from the bottom to top we are, okay? That would determine precisely where we were on the flat Earth. Won't work on the Earth's surface. So what we need here is a dividing line, okay? And how we do that precisely, we can determine the axis of our rotation, okay? North pole here, south pole there, that's where everything spins around, okay? We can identify those with a fair amount of certainty. Okay? Halfway between the north and the south pole, in any direction, you get what is called the, now your equal distance from the poles. And that place is called the, sounds like equal? Equator. Exactly. That's where equator comes from. Equal. So at that place, we'll count that as our 0 degrees. North or south, it doesn't matter. As we go toward the North Pole, you go up by 10 degrees from 0 to 90. As you go south of there, you go 0 to 90 south. So you can't get any further from the equator than 90 degrees. That's the North Pole or the South Pole. Those are called our parallels. And you'll see them on the globe. Those are your parallels. Now, the ones they showed are 20 degrees there, which only gets you up to 80 and then another 10 degrees to the north. On a lot of globes like this one, they'll be at 15 degrees. So there's the equator. There's 15 north, 30 north, 45 north, 60 north, 75 north, and finally 90 North Pole. Same thing to the south, 15 south, 30 south, 45 south, 60 south, 75 south, South Pole, 90 degrees south. So that's one half of the picture. How far you are north or south of the equator. That gives you one dimension. That's how far, how from the top of the page or bottom of the page. That gives you one piece of information. But if you know what parallel you are on, you could be anywhere on the surface of the Earth on that parallel. Okay? Now remember, there are ways to determine that. Noon, elevation of the sun at any given time, and the celestial equator, how far it is from that, and that can give you, you can find out some things there. Even better, Polaris, okay? Find that, shoot that at any time. That tells you exactly the parallel that you're on, okay? Exactly. You have to have a sextant to do that, and the North Star Polaris is not a very bright star, okay? Now, here's another way of looking at that. Imagine you had a tractor across the center of the Earth, and how far up or down, up from the equator you are, how many degrees that is, that gives you your parallel, your latitude line. Okay. Now, this verbiage here doesn't match the picture at all. That gives you north-south location, so you could be anywhere around the surface of the Earth on that latitude. You need something to give you an east-west dimension. What we use there is the prime meridian. I think we talked about that before. They just sort of arbitrarily chose, and probably because this is back when Britain was the queen of the oceans, okay? The British Empire, the sun never sat on the British flag, on the Union Jack. Britain was the big honcho power broker in the world. So they got to choose where the prime meridian was. And since they were honcho in the naval, they chose the Naval Observatory at Greenwich, England. That's just a little bit east of London. I think I told you the story already. My wife took, it started off being a simple trip. She was going to take her niece, and she was going to a meeting in Paris. She was going to take her niece to the meeting, and then they were going across from Paris to the Channel to London, and then back again. And when Karen's mom, her niece's grandmother, found out they were going, I want to go. And then when Karen's sister found out she was taking her brother's daughter, well, Michelle and I want to go. So after a while, she had an entourage. So she took her mom, her sister, and her two nieces, and they went over to, I can't remember where they flew to and from, but they went both to London and Paris. And when they were in London, they got to go one day to the Naval Observatory. They wanted to go see, I don't know why they choose there, they just had a tour and they went there. It happened to be a day that they were opening a new building, and it's the Royal Naval Observatory. So technically, it doesn't belong to the Queen, but she's in charge of it. And so she came to christen the building, to dedicate the building. So that day that they were there, the Queen happened to show up, so they got to see her drive by and wave, part of their standing. So they were pretty cool. So the Royal Naval Observatory in Greenwich, England, which is right there, just a little bit east of London, that's where they chose to be the prime meridian. And from that point, from the North Pole, the great circle that goes through that, crosses the equator, goes to the South Pole, that's the prime meridian, meaning the first meridian, the main, where you started from. And then what you do from there is count 180 degrees east or 180 degrees west. And that gives you your second locator. North and south is latitude, east and west is longitude. Okay? From the prime meridian. Now that puts another pretty important line in the backside, exactly opposite the prime meridian. Does anyone know what that meridian is called? It's the same meridian, but just on the opposite side of the globe. You want to know what that's called? Strange name, the International Date Line. Why would they call it that? Because remember, the Earth is spinning. Okay? Right now, it's a little after 1 o'clock in Birmingham. That means it's probably a little after 7 o'clock over there in England. That means it's a little after 11 o'clock on the West Coast. And to go on. So you see, it's earlier in the day this way, later in the day that way, and somewhere over here, it's one day and the next day across from each other. Because it's earlier in this day here, later in this day here, where they meet, they're a day apart. Okay? That's why it's called the International Date Line. Exactly opposite the prime meridian, that's the International Date Line. Okay? Now, that's the meridian that it's on. It does take a few jigs and jags along the way. For instance, that international date line going down here would cut through the western part of Siberia. That means this part of Russia would be one day and that part would be another day. They didn't want that to happen. So they jig it a little bit to the east so they include all of Siberia in the same day. But that goes right through the Straits of Alaska, the Bering Strait, and then we have the Aleutian Islands that come way out here. On the other side of the international line, so once it makes it through the Bering Strait, it has to come out and incorporate all of the Aleutian Islands and keep them on the same day as the rest of Alaska. So it makes another jig there. Then it goes pretty much due south until it gets down here around the Samoan Islands. And they try to keep as many of them at the same time, so it goes out here to include most of them on the same day. And that includes New Zealand and some of its outer islands, and then it comes back in and goes into the South Pole. So there are some deviations there on the backside of what the international date line is. But that meridian there is 180 degrees east or west on the opposite side, and it forms the basis for the international date line. So anywhere east of England, London, England, basically, is going to be so many degrees east from 0 to 180, and anywhere west, where we are, is 0 to 180 west. Where is Birmingham? Obviously west of England. Here's England. We're west of England, okay? And we are awfully close. There's Birmingham right there. Oh, there's Montgomery. Birmingham's up here. We're in the upper 80s because the 90-degree meridian, exactly 1/4 of the way from London, England to there, halfway to the international date line, that goes through awfully close to New Orleans, Jackson, Mississippi, Memphis, Tennessee, St. Louis, Missouri. Springfield, Illinois. Madison, Wisconsin. Green Bay is a little bit further away. So that's the 90 degrees. We're a little bit east of that. So we're at 80, I don't remember, 88, no, more than that, I think. 83, 85, something like that. Okay. West. Okay. Now, our position on the Earth is in a intersection between the parallels and the meridians. Okay? That defines exactly where we are with respect to the rotation axis. Rotation axis defines the equator, so that defines that, and then the arbitrary choice of the prime meridian, how far east or west of that. So the parallels measure your latitude, how far north and south you are from the equator. Meridians measure your longitude, how far east or west you are from what? Meridians. What would mean first or main meridian? Prime meridian, exactly. Okay. So here again, your parallels measure how far north or south you are of the equator. We happen to be around 33 degrees, 23 minutes, 45 seconds north of the equator. So we would be somewhere right about there, okay? Okay. 23 and a half is the Tropic of Cancer. We are a little bit above that. Okay. And this again is showing that from cut away apart to the Earth, it's how many degrees you are north of the celestial equator. That would put us right about in there. Okay. Then, east-west, you have to pick somewhere to begin. Easy to pick the equator, equal distance between north and south. There's no equal distance between anything, so you just arbitrarily, they chose, because Britain was the honcho, she chose Greenwich, England to be that. So there's 0 degrees there, going to the west, 20 degrees, 40 degrees, 60 degrees, 80-some degrees, we're way over here, almost a quarter of the way around the globe from Greenwich, England. Okay? And here they show it cut away. This is on the east. If you cut away on the west, it would be on our side. But this would be places like France or Germany, and you just keep on going around until Egypt would be somewhere in here, and India and stuff, and finally you get in the Pacific back there. Okay. So that identifies place. Now, special parallels are climate related. Why do you think that would be the case?
Because of the special parallel.
Yeah.
Because of the sun?
Yes. Okay. What two parallels determine where the sun is any time of the year? Somewhere over these two parallels, between these two. The dotted lines here, and dotted lines here. Yes, the Tropic of Capricorn to the south, Tropic of Cancer to the north. Anywhere in there, warm climate all year long. Okay? Because that's in the tropics. The sun's directly overhead, somewhere inside those two parallels. Two other parallels that determine climate.
Poles? It's not poles, but
What?
I see the poles, but
Yes, near the poles. So what are those two parallels? They're called circles.
north to south.
Arctic, Antarctic. Arctic circle up here, 23.5 degrees, which is 66.5 degrees north to 90, and 63.5 degrees south to 90 at the Antarctic. So those are the special parallels that are climate related. And those are exactly from the tilt of the Earth. Okay? 23.5 degrees north is Tropic of Cancer. 23.5 degrees south, Tropic of Capricorn. 66.5 degrees north is Arctic Circle. 63.5 degrees south is the Antarctic Circle. All based on that 23.5 degree tilt that the Earth has. So, inside these, very warm all year long. Outside those, extraordinarily cold all year long. And here, moderate, temperate. Okay? Now, in a sense, these areas here are the really only ones that really have 4 seasons to speak of. It's so warm in here all year round, you can't tell much difference between fall, spring, summer, and winter. A little bit. Usually what makes the difference here is how much rainfall you get. And they say they go by the monsoons. Okay? It's either the rainy season or the dry season. That's how they talk about seasons there. Up here, it's whether you have daylight or darkness. Okay? That's about it. You're cold all year long. I mean, the temperature changes some, but not a lot. Okay? In here, it's fall, spring, summer, and winter. The further south you are, the less difference. The more north you are, a little bit greater difference. We're right, not quite in the middle. We're just barely above the southern part, so we don't see. We have much more distinct summer and much less important winter because we're so much closer. Okay? Make sense? All depends on the sunlight coming in and what angle it hits us. Okay, so that was place. Here's time. Okay? The time interval, like we said before, solar day would be between the time the sun crosses our local meridian, that's the transit, highest point it will reach that day, from one day to the next day. That's one solar day. Okay? So that's one thing that we do. Okay? And that's going to be approximately evenly spaced. Not quite. What? Figure 8 shape shows some deviation in that. We did it in the last lab. What's that shape? The word means sundial, but it's not like our normal sundial. It's an A word. Analemma. Very good. Analemma. Okay? That will mean they're not exactly evenly spaced. We make them evenly spaced, but this moon may not be exactly at 12 o'clock. Okay? Okay. Astronomical examples, the rotation of the Earth on its axis, that makes what? One turnaround makes, definition for, 1 day, 24 hours. Okay? One revolution of the Earth around the sun makes for one revolution of the sun around Earth around the sun makes for 1 year, which is about 365.25 days approximately. So these are the basis of the day, the year. The season, what does that depend on? The tilt, combined with moving around the sun. So how about the month? We didn't talk much about month. What word do you almost see in month? Moon, that's exactly. So this has nothing to do with the sun or the tilt of the Earth or anything else. We define our months approximately by a full cycle of the moon. Not exact, but close. Okay? So that's where the months come from. But all come from astronomical examples. Okay? So different ways of measuring days, months, and years. Days from our spin, months from our rotation, years from our rotation, months from the moon's phases, moon's cycle. Okay? So did anyone need that longer? Okay, sorry about that. If I get going too fast, slow me down. Stop me. I don't mind sitting for a bit. In fact, it feels good. You got it? Everybody got it?
Yeah.
Okay. All right. So let's look at daily time. And we talked about this some in the last lab, I believe. Let's look at the sun, Earth-Sun motion viewed from above the North Pole. So you're somewhere up in the Oort cloud looking down at the Earth going around the sun. Okay? The Earth revolves counterclockwise around the sun. Okay? It rotates in that same direction. Okay? Counterclockwise as you're looking down on it. Of course, it'll be at a tilt, so it's not exactly on that. So what does that mean for us? We think the sun rises in the east, just because we're spinning one way, and sets in the west. Well, that's because of how we're spinning. If you picture this, Chrissy's going to be the sun again for us, right? Okay? When Birmingham, Alabama is right there, it's right at the edge, and spinning this way, that's when the sun rises. Already rose in Atlanta a few minutes before. So the sun rises in the east, because that's the eastern direction, and then it gets to midday, and then sets in the west. Okay? Because that's the western direction from here. Okay? And that's about, depending on what that time of the year it is, about 12 hours later. Not exactly place. Okay? So that's why all this is determined by our motion. I mean, guess what? You can't make up these seasons and everything else any other way except this model that I've seen or can even imagine. Okay? Now, here's a problem that comes with that. Okay? The Earth is moving from one day to the next around the sun, which means we've traveled a distance. When this is noon right here, when the sun's directly overhead right here, and we move a little bit this way and the Earth spins, when it gets right back exactly the same place it was here, the sun's down here now. It has to spin a little bit more. We did this in the first two labs. We calculated how many minutes that is. That it has to spin a little bit further to catch the sun. It's about 1 degree. The reason it's 1 degree is it takes us 365 days to go around the sun, and there's 360 degrees around the sun, so it's a little bit more, but not much more than 1 degree. And how long does that take for us to do that 1 degree? We did it. One of the first questions on both labs. How many minutes was that? 4. About 4 minutes. That's the additional time that it takes to turn back to being a solar noon. So if we were using some star out there to be our noon, that star, let's say we'll do it at nighttime, that star would be directly overhead here and here. That would be what we call a sidereal day, one based on the stars. That would be 4 minutes shorter than a solar day. Because the sun, we're moving around the sun, and we're not changing with respect to the stars. They are so far away. There's no motion around them. But that little bit that we move there, nothing compared to them. So a sidereal day would be about 4 minutes shorter than a solar day. And that's what we're talking about here. The sun's motion across the sky. Noon is technically the time when the sun is at the celestial meridian, your local meridian. That would be technically when noon is. No matter what the clock says, okay? That would be when you're... Thank you. In the Navy, we call that the local apparent noon, okay? The book calls it the apparent local noon. We call it LAN, local apparent noon. They call it apparent local noon. I think the reason is nowadays LAN stands for something else. And so we used to call it LAN, local apparent noon. Whatever you call it. So that's your noon at a particular longitude. Anywhere on that longitude line, your noon will be at the same time. North, south, hemisphere, it doesn't matter. Okay? Now, The apparent local star time, that's given by what I call sidereal time. We'll talk about that in the next lab. Or that wasn't in this lab, was it? I don't think so. I think it was next lab. Okay, it's given by the position of the sun in the sky. Oh yeah, I'm sorry. That's local apparent solar time. That side over there is going to be. No, this is all solar. Okay, sorry. Given by the position of the sun in the sky, can be measured with a gnomon, which is another name for sundial, and a lemma is yet another one, but that's not. This is a gnomon. It's not the time that's shown on clocks. Clocks that divide it into 24-hour days, no matter what. Okay. What features change the local time from the clock time? 2, maybe 3 major features. One is that the Earth's orbit is not circular, it's elliptical. Sometimes we're moving faster, sometimes we're moving slower. So that's going to make one little bit. The other part is since we're tilted, okay? And that also contributes some. And the analemma, remember, its height is determined by how much tilt there is in the Earth. The fatness, that's determined by how fast we're going around the sun. When we're closer to the sun, we're going faster. When we're further away, we're going slower. So that gives us what we call mean solar time, the time averaged over the apparent solar time. So do it over 365 days a year, that's going to be about. Now, it's averaged over 2 effects, and this is what I just said, the Earth's orbital speed, which changes through the elliptical orbit. Now, when are we closer to the sun? About what month? January. So in January, we're moving faster relative to the sun. Okay? Well, just moving faster. Okay? And when are we farthest from the sun? In July. And then we're moving more slowly. So then, that will make our local apparent noon change it a little bit. And then the other thing, the equator is inclined to the ecliptic. So that makes for another variation. So the mean solar day is about 24 hours. That's what we use, 24-hour average from the mean solar times, all the 365 days of the year. That average will give us about 24 hours mean solar time. Okay? That's what we base our clocks and everything on. Okay. Now, here's where I thought we heard before. What is a day? It depends on what your reference is. It's the length of time for the Earth to rotate once on its axis. Well, that's not quite a solar day. It's 3-4 minutes short. That's a sidereal day. You rotate once on the axis. Remember that illustration? That would put you here, but the sun's not at noonday at that time. That's a sidereal day, based on the stars. Interval between 2 consecutive crossings of the celestial meridian by a particular star. So if you found that brightest star out there, Sirius, say, and saw when it crossed your local meridian, the highest point it got in the sky one night to the highest point in the sky the next night, it's a little bit less than 24 hours. 23 hours, 56 minutes, and so on. The little variation is because of the Earth's constant rotational rate. Okay? We say constant over millennia is constant, but over a really long period of time it's not. So the apparent solar day is the interval between 2 consecutive crossings of the celestial meridian by the sun. That involves our revolution around the sun and that extra bit of rotation we have to catch back up again. About 4 minutes longer than the sidereal day. Now, they've got this in the wrong place. This should be over here. 23 hours, 56 minutes, and 4 seconds is a sidereal day. The solar day is 24 hours. And that was at the bottom of the last one, right there, 24 hours. So they sort of got, whoever did the graphics here got things a little off. Probably not the scientist who wrote the book. Okay. Anyone need that a little longer? Okay. Now, equation of time. That sounds like a pretty hefty concept, doesn't it? This traces the yearly variations between the apparent local time and the mean solar time. It's not going to be exact. Hardly any time. Maybe 4 times a year they'll be on the money. And this appears as a figure 8 on the floor. Remember I talked about that. Okay? That if we were to cut down the trees outside and block off both windows, except to have a little bitty hole, maybe about the size of a quarter or so, for the sun to come through, and every day when the sun reached its highest peak, if we made a mark on the floor of where the sun shone to be at that time, and did that 365 days for a full year. Of course, cloudy days we wouldn't see what that was, but on most days we would see it forms a figure 8 on the floor. Okay? Now, 2 effects. The axis tilt, that is going to be greatest in the summer. Well, let's see, the sun will be highest in the summer, so it'll be the closer to the wall then, and greatest in the winter when it'll be further from the wall, the sun will be further down. So that's the axis tilt. That's your north-south motion. Okay? And here's Chicory, right? All right. Only missing guy. Where's the guy, huh? And this has been the second week that we haven't seen him. Was he going out of town? Did anyone say? Did anyone hear him say? Okay. Now, the second feature that affects this is how fast the Earth's going. Now, they say orbital speed. I think the better phrase there would be revolution speed. Orbital tends to see, I guess that's right, orbiting around the sun. So, yeah, orbital speed, that's right. Not rotation speed, but orbital speed. And that gives you your east-west variation when the time is slower or whatever. Okay. So the equation of time is that cumulative plot, that figure 8 that we get. And is that coming up right now? Well, not quite. Close. First, what we see here is the sun's path. This is where the sun is on about March the 23rd. This is where the sun is above the equator. I'm sorry. June the 21st, March the 21st, the sun is directly overhead down here on December 21st, and then March 21st is right there. So March 21st here and there. It's a little bit extra because you see Siberia is here and here. Now, not quite the analemma, but getting close. Okay, this is even closer. Okay, this is how much before or after behind the clock is behind the sun shown on the sundial. Okay, and you see around June and July, okay, right in there is where the Earth is spinning the slowest. So the deviation is the least, okay, where Earth is spinning, not spinning, traveling around the sun. No, this is, slowest, because we're farthest from the sun here, so the deviation is less. When we're going faster, that makes the deviation more, and that would be, should be about January. We're sort of okay now, on this. Now, if you were to take this and fold it over like this, there you get your figure 8. Okay? If you were to take this and fold it right over this line right here, see, this would complete that, this would complete that, and you get your analemma, that figure 8. So we're awfully close to it there. Let's see. They don't show it, do they? Yuck! It's in your book, okay? Oh. Let me see what table 16.1 is. Oh, this is interesting. I hadn't noticed it. I taught from this book last time, but I didn't notice this. Where do we get the names of the days of the week? In English, the day of the sun is, say again? Sunday. Okay? The day of the moon would be Monday. The two biggest celestial bodies, apparent anyway. Okay? The day of Mars, in some other language, that would come out Tuesday. And I don't remember what language that is. Latin, maybe. But in the French, it's Mardi. Okay? Now, does anyone know why you should be able to remember Mardi in French? In the spring, when everybody parties in New Orleans and Mobile. Mardi Gras. And what does the gras mean? It's spelled like gross, which means big. It means Fat Tuesday. Mardi Gras. In French, they give the noun first and the adjective afterwards. So all the other languages sound much more like Mars than English, where it's Tuesday, some other deity that was in place of Mars. And then the day of Mercury, and again, the other days make more sense. It's Wednesday. Where we get that, I'm not sure. The day of Jupiter, and most of these don't sound like it. 3 of them do, sort of. That's our Thursday. The day of Venus, and 4 of these sound more like Venus. The other doesn't. But that's Friday. Freer's Day. Freer is, I think, the Greek correlation to Venus. And then what would be Saturn's Day? Saturday, exactly. Okay. Which also is where the Sabbath comes from, meaning the seventh in some senses. Okay. So I failed to see that last time I taught the course. There are some questions here which are just dinky little make-work math days. But how many sidereal days are in 1 year? Well, you know how many solar days. It's 365. A sidereal day, a solar day is 24 hours. A sidereal day is 23 hours, 56 minutes, and 4 seconds. So if you do those calculations, you can come up with it. But man, it's just a lot of busy work to do that. So I'll let you look at that. If you want to do it, go for it. I don't know. I don't care. Okay. Then in your book, and I'm sorry they didn't show it on the slideshow, this is what they meant. If they had, mapped out the Earth, the sun's not shadow, but the point of the sun at noon each day. Farthest over here would be December, and the closest over here would be June, and then the thickest part is where the Earth's moving faster, and the thinner part is where it's moving more slowly. Okay, so that gives you your analog, which is another, in a sense, sundial. Okay. And then there is a little blurb here on daylight savings time. Now, I don't know what y'all think about it. To me, it's a pain in the neck, but a lot of people love it. Okay, I think that's the bankers, because they like to golf, get off earlier in the day and golf afternoon. the summer. I didn't say that, did I? But no. And the politicians maybe, I don't know. They blame it on the farmers. I don't think the farmers care. Their days are what they are. I know that the right next door to our farm in Georgia was a dairy farm. It isn't any longer. But boy, when they went on daylight saving time, that meant they got up at 4 o'clock in the morning to start milking the cows rather than 5 o'clock in the morning. I don't think they particularly liked it either. But everybody blames it on the farmer. But you can read that, and if you want to talk on that, that would be fine too. Now we're moving to what we call the standard time zones. Okay? Now if you think about it again, there are 360 degrees of longitude around the globe, right? One full circle is 360 degrees. How many hours are there in a day? 24. If you divide 24 into 360, that means each hour occupies 15 minutes of that 15 degrees out of that 360 degrees. That means for every time you go 15 degrees longitude, you're going to go up or back 1 hour. Now the trouble is they measure this from the center. Okay? Okay? So the center of what they call Greenwich Mean Time, the one that goes through Greenwich, England, that's going to be at 0. So it's going to be 7.5 degrees on either side of 0. So it's 7.5 degrees east, 7.5 degrees west. That's Greenwich Mean Time. Okay? Everywhere in there is going to be on the same time. That's that. And then every 15 degrees from there, which is 7.5 degrees on either side of 15, 30, 45, and 90, we're in, I didn't count that right, but here we are. This is around 75 degrees, 7.5 degrees on either side there. That basically is our eastern time zone. Now, part of Maine is outside that, but we pull it in and count them. They're technically in Atlantic time, but we count them in eastern time. And then 7.5 degrees on either side of 90 is going to be central time. And that's why Atlanta is just on the other side of eastern. We're just on this side in central. Okay? But they use the state line, which, and from what I understand, I don't know know anyone from down around Opelika, Alabama? It's not quite Opelika. What's in the other town? Something City, Phoenix City, Alabama. Anyone know anyone from there? Phoenix City is just across the state line from Columbus, Georgia. Columbus, Georgia is a pretty big city. Phoenix City is not nearly so big. And Columbus, Georgia has a huge army base. Fort Benning, is it? Yeah, Fort Benning in Columbus, Georgia. And Phoenix City is right across in Alabama. Because a lot of people in Phoenix City work in Columbus, Phoenix City stays on Eastern time and does whatever Columbus does, so they're not an hour off. And that happens in a few places around. So that's what it means by adjusted for local consistency. One thing we do, we count the state line, so one state isn't another, but even more local consistency, because Phoenix City counts on Columbus for a lot of their employment, they'll stay on the same time zone there. Now, daylight saving time, that's what that little drawing was about. We set the clocks ahead in the spring and back in the fall for that 1 extra hour of daylight during the summer evenings. Who cares? I mean, it's still going to be hot. It's still going to be whatever. What I especially don't like is how early in the spring they do it. They don't wait till equinox. They do it even before that. And when I was in high school and riding the bus, I lived way out in the country, and we had to catch the bus around 7 o'clock in the morning. And it would be still dark and still pretty cold when they went to daylight saving time. We had to be out there in the cold, in the dark, to catch the bus. And that I really learned to hate it. Okay, I think that still sets things for me. All right, international dateline, we've already talked about that. The 180-degree meridian is designed to correlate within the 24-hour time zone. Now, here is an anecdotal story. I don't know if this really happened, but it was one that you used to tell in the Navy a lot. Okay? In the Pacific Ocean, which is where the international dateline is primarily, supposedly somewhere in here there is an island that sits smack dab on the international dateline. And supposedly some entrepreneur bought the land sitting right smack on the international dateline and built his bar right smack crossing the international dateline. Why did he do that? So when it was Sunday on one side, it was Monday on the other side. He would close the bar on Sunday, open it on the other side on Monday, on that same night. And then on the other, when it turned Saturday night on one side and turned to Sunday, then he would move the bar over here, and so he could stay open on Sundays and half of his bar was on Sunday and half was either on Monday or Saturday, whatever. So he was always open half his bar. Whether that was really true or not, I don't know. But people love to tell that story. He built right on the international dateline because on Sunday, always one half of his bar was open. Whichever time, night, morning, or evening, he could stay and flip-flop. Okay. Dumb story. All right. So this determines our time zones. And like I said, centered around 75 degrees west is their Eastern time zone. Like I said, part of Maine falls into Atlantic, but they adjust that for local purposes to keep all of Maine in Eastern time zone. Now, the Central time zone line, it's all wacko. I think they got this a little wrong. Well, no, this is somewhere right down in here is Phoenix City and things. They didn't show that. That's just a very little area. Poor old Florida, because it's such a long panhandle, and their things are more related here. This part of Florida is on Central, that part of Florida is on Eastern. Okay? Tennessee, such a long state, right around Chattanooga. I don't know which side Chattanooga is on, Central or Eastern, but it's Central or Eastern, but it's right on that. Nashville's over here, so I know it's Central time zone. Knoxville, I think, is on Eastern time zone. Kentucky, same way. Part of Kentucky is on the east, and part is on Central. Now, this part of Indiana chose to be on Central time zone. Why? St. Louis is right there. Right? St. Louis, no, that's too far down. What is the city that's there? I don't know why. They just decided to be up here. Chicago, Illinois is right here. Because much of this area commutes to Chicago, they chose to be in Central time. Okay? Poor old Michigan. Michigan is this peninsula. Up here is Upper Michigan, Upper Peninsula Michigan. So it's on Eastern time zone because most of Michigan is, but it should be on Central time zone. Okay? Minnesota juts out, so it's the same. Now, why in the world North and South Dakota, it looked like that fell right down the line, but it's because this half of North and South Dakota pays attention to what's going on in Minnesota. This half pays attention to what's going on to the west side. So they split down the middle. I know here, Denver's here, so this side of Nebraska, when they go to the big city, they go to Denver. They don't go over here to Lincoln and Omaha. It's too far. So they chose to stay on Mountain Time. Same thing with Kansas. Texas is part over here. Santa Fe, New Mexico is the big draw here. So since New Mexico is Mountain Time, this end of Texas also goes with Mountain Time. Same thing up here, Idaho. Part of Oregon stays with what Idaho is here, but part of Idaho stays where Washington is here. So they flip-flop back and forth. Montana gets split. Well, this is the edge one. This is Idaho. And then they don't show, but Hawaii's out here on a different time zone. And Alaska probably has 2 or 3 time zones of its own. Well, it's not that big. I mean, it's the biggest state, but why would it have more time zones? Here is 15 degrees near the equator. Here is 15 degrees near the equator. Look what 15 degrees here. Okay, it's a lot narrower because these lines are all going to the North Pole. So you change time zones more frequently when you're traveling here than you would if you're traveling down here, because you got further to travel because the slices of pie get thinner. So Alaska, I take that back. I bet you they're all on the same time zone. Well, probably not. Aleutian Islands, I don't know, because the 7.5 degrees would be right here. So that would cover all this part. This part down here, I don't know. That should be on this time zone, and the part over here really should be on the next time zone. So they could have 3 time zones. I don't know what they would do. But Alaska is sort of strange because way down south here and way from east to west, that's a long state. But those are islands and peninsula and things like that. So that's what they mean, varied by local practices, local consistency. Okay. These are the approximate time zones nationwide. Oh, this is showing the international date lines, which I showed you on the map. It should be following 180 degrees because Siberia is east of that. They included that on the previous day. And because the Aleutian Islands come out here, they include all them on the next day. Okay, so it comes down. Then it goes pretty straight here until it gets to some of these islands down here. Mostly New Zealand islands, but some of the other archipelagos of islands, they want to stay on the same one, so they jut out here and then come back. So that's why the international date line isn't quite as straight as it should be because of local consistency. All right, why don't we do that? I'll pause this for now. Let's try to keep it 10 minutes or less, okay? And we'll come back because this is time. We should have stopped it at 1:50 and had a break until 2, but I went over a little. Now, where we are now is in Chapter 16. We just finished talking about time zones, so we're just about on page 421. That figures on 421, and we're just about to talk about yearly time, okay? So here's yearly time. 2 types of yearly time, just like there's 2 days. There's a solar day and sidereal day. Solar day based on the sun, sidereal day based on the stars. Solar day is about 4 minutes longer than a sidereal day. Okay, we have 2 types of years then. Now, why don't they call it a solar year and a sidereal year? I don't know. They call it a tropical year and a sidereal year. The tropical year is the interval between 2 consecutive spring equinoxes. So when the Earth is on its revolution around the sun, when it gets to the spring equinox 1 year, that's when it starts, goes all the way around the sun again. When it hits the disk, it gets back here to the spring equinox the next year. That's called a tropical year. And I can't tell you why, okay? And it's about 365.24220 mean solar days. Now, what's the ramification of that? It's not exactly 365 days. In fact, how much over is it? Almost. Almost a quarter of a day. 0.25 would be a quarter of a day, wouldn't it? So that means that what happens every 4 years? Leap year. We add another day on February 29th. Don't have a February 29th, but once every 4 years. But that's a little too much. Okay? Because you're off by 0.5780 days. Okay? So not very much, but a little bit. So here's what we do. Okay? Every decade, no, not decade, every century that ends, okay, the centuries. The next one coming up is 2100. The last one we had was 2000, right? And there's 2200, 2300. Now those are all four, okay, and by the way, let's go back to our leap years every 4 years. So every year that's divisible by 4 would be a leap year, wouldn't it? And Jordan's here. We got 100% attendance. Way to go. Okay? So, this is 2018, not a leap year. 18 is not divisible by 4. 2016 was, the next one will be 2020. On those years, we'll add an extra day on February 29th. But if the century is divisible by 4, like the last one we had was 2000. Okay? Next one we have is 2100. I probably won't see it. Okay? All right. And then there will be 22 and 23, then 2400. On those, even though those are technically leap years, they don't add a day. So if you go back to your calendar in the year 2000, even though that should have been a leap year, they won't, because this isn't quite 0.25, it's 0.24220, okay? So every 4 centuries, we don't add a leap day on that year. That's evenly divisible by 4. So we didn't in 2000, and we won't again in 2400, okay? But I won't be around to mark that on the calendar. But I did get to see one during my lifetime. And a year divisible by 4 that we didn't have a leap year. So that's the tropical year. The sidereal year is the interval between 2 consecutive alignments of the Earth and the Sun relative to the stars. Okay? So that isn't necessarily our equinox. But let's just say on spring equinox of this year, okay, you're going to be the sun force now, all right? Okay, so spring equinox this year, and we go around the sun again, and spring equinox the next year, the stars may not be quite in the same alignment because we're moving, remember, the whole solar system is moving down up that spiral, helix they call it. So the interval between that, it's not much, but it's only about 20 minutes longer than a tropical year. 20 minutes out of 365 days, okay? That's pretty small, okay? But a sidereal year is just a tad longer than a tropical year. But we don't care about that. We pay attention to the sun, not to the stars, okay? Now, there are adjustments to keep the current calendar year up with the seasons, and that's the leap year we talked about. They talk about leap seconds, which make no sense to me at all, but I guess you could do that every now and then. Rather than doing a leap year, just have an extra second every day or so, and then make up the whole. That's kind of crazy. How could you do clocks that help up with that? So anyway, those are our adjustments. Okay? Now, that's the yearly. Remember, sidereal means stars, solar means sun, and for some reason tropical means sun too. Okay? But we got one other type of time. And remember, the month, that's based on the moon. Okay? And we have 2 types of months. One's the sidereal month, based on the stars, okay? That's consistent through here. The other is the synodic month, and I don't know where that word comes from either, okay? It's not solar because it's lunar, but what's that synodic? Well, here's what it is. The sidereal month is the orbital time measured with respect to the stars, but that's the orbital time of the moon around the Earth, okay? So on this day, the Earth is here, the moon's there, okay? The moon's going around the Earth, but also the Earth is moving around the sun, right? So Earth's moving around the sun while the moon moves around the Earth. When it gets back to this day, okay, that would be a sidereal month, where the moon is lined up with the same star it was on 1 month earlier. That's only 27 1/3 days. But you see, we don't base ours that way, sort of. We go on full moon to full moon, because the moon has to travel a little bit further to line up with the sun to be a full moon. That makes our synodic month, which is based on the phases of the moon, 29 1/2 days, okay, as opposed to 27 1/3 days. So that's 2 1/6 days longer. So the synodic month is, that's the biggest difference between the sidereal and our synodic. And that's because the moon is going around the Earth faster than the other things are. Okay, so it includes the facts of the Earth revolving around the sun and the moon revolving around the Earth to give us the next full moon. Now, what does that mean about the dates? We can't make a month 29 1/2 days. That would just really mess up our calendars pretty badly. So it seems like the reasonable thing to do would be make half the months 29 days and half the months 30 days. But that's not what we do, is it? How do we do that? We make 7 months 31 days, what? And 4 months, 30 days, and then have 1 month, 28 days? Who came up with this? I don't know, but that's what we do. Averages out to about 29 1/2 days a month, okay? But it's nowhere regular. Now, how do you remember which day has which month has how many days? There's several little things that people sometimes use. What's that? The knuckles. I had never heard that. I'd always had to go through the little song. 30 days, that's September, April, June, and November, all the rest of 31, except for February, which is blah, blah, blah. Much easier to use the knuckles. Start on a knuckle, and that'll be January, 31, big knuckle. February, small, 28. March, 31. April, 30. May, 31. June, 30. July, 31. Then start over because you don't have enough knuckles this way. August, 31. Back on the knuckle again. So July and August are 2 back-to-back 31s. September, October, November, December. Then December and January are back-to-back 31s. Okay? So that is the easiest way I've found to do it. Or look at a calendar and see how many days are in the month. That's the other thing. Everybody has a cell phone. You can just ask, what's her name? Siri or whatever. How many days are in this month? Yeah. She'll tell you. Oh, she. All right. Any question on monthly time? And again, why? Sidereal always means according to the stars. Solar day, tropical year, synodic month. Okay? Why they don't have a fixed name for those, I don't know. Any questions on monthly time? Okay, now this pulls us into the moon. The month is a good segue to get to the moon. The moon is by far our closest neighbor. Okay, it goes around us. Okay, it's the only satellite naturally occurring satellite that we have. It's 380,000 kilometers distant, which is a pretty far piece. That would be about 200,000 miles away, approximately. Okay? Characterized by craters. What would that mean to you? Second?
Water.
No, craters doesn't mean water. Craters means
Meteors.
meteors have hit it, and why would there be so many craters? Why don't we have a lot of craters? We're bigger than the moon. We would get hit by
Once they
meteors.
hit the atmosphere.
Because we have an atmosphere, the moon does not. That's it. When you see anything with lots of craters, figure no atmosphere or very little atmosphere. Okay? Then the moon is also characterized by highlands, maybe not quite mountains, but close to it, and Maria. Now, where that got its name, when they used to look at the moon and they could see what they thought were the highlands and then the broad places that are not highlands, they thought there was actually water there. That's from marine, meaning water. Okay? It turned out there's no water there, not to speak of. These are the ancient lava flows. So the fact that there used to be lava flows there, what does that tell you about the moon? The moon was seismically active, okay? Meaning they had moonquakes, they had volcanic eruptions, they had things going on. Not for a long, long time. We'll get to that a little bit later. So the craters, no atmosphere. These two things go hand in hand. Lots of craters, meaning no atmosphere. Now, we have sent 12 Apollo missions to the moon. Maybe not all the land, but to be close to the moon, to orbit the moon, to go around the moon, and take pictures of the moon, that kind of stuff. There were many more Apollo missions than those, but those were the ones. The early Apollo missions were to get ready to go to the moon and to test out equipment, things like that. But only 12 actually made it there. One of these, and remember the numbering is not in accordance with this, what was probably the most, well, let's just hit it. Here's a picture. Now this is a composite picture of several. I think this is pretty close to what you see on the on your thing. But you see the highlands are sort of the light colored areas, and the dark color area do look like seas, don't they? But they're not. They're ancient lava flows. They're relatively flat, no mountain type areas, but you do see it, and it's sort of harder to see the speck and potted pit, whatever you call it, with craters. Okay, marred craters all over it. And this picture doesn't show the craters as well as some. Okay, and that's the big picture you see on your book on page 423. Okay, now they talk next about. All right, before I get there, let's go back. I wanted to say this. When they mention the 12 Apollo missions that actually went to the moon, there were many more Apollo missions. Okay? The Apollo spacecraft did not start off well. Does anyone know what happened with Apollo 1? It's what?
It caught on fire.
Yes, it did. On the launch pad. They weren't even really going to launch. It was the crew died in the spacecraft during a test 3 weeks before they would have flown into space. It was a huge shock. Here we were ready to go to the moon. Remember, President Kennedy had said we'd get there in a decade. NASA had been really pushing at it, and here they were just doing some tests. There was some sort of a short of something, and fuel caught fire. I don't know what happened for sure. I'm sure they do, but I don't know. And anyway, the 3 astronauts on board died. Now, if you were to say, what's the most space-related city in Alabama? Huntsville, absolutely. The Marshall Space Flight, no, is that it? Whatever, they have, big space center there. NASA as big. Second?
The space and Rockies.
Yeah, the Space and Rocket Center is certainly there. That's the sort of the tourist attraction there.
Marshall's.
Marshall, it is Marshall. Okay, I thought it was, but I didn't want to mix it up with the one in Texas. Okay, so the Marshall Space Center is there. Okay, so Huntsville was really shaken by Apollo 1 disaster. If I read the names, are any of you at all familiar with Huntsville? Okay. You were born in Huntsville. Where did you go to school in Huntsville, did you?
AAA, then Lee High School.
Okay. But you'll probably recognize these when I read the names. The 3 astronauts that died, Gus Grissom. Grissom High School is one of the big high schools in Huntsville. It was the first high school built after that disaster. They named it after Grissom. Ed White.
Another school.
That's another school. I think that's a junior high school. Okay. And then Roger Chaffee. I think it's elementary school. So they named the next 3 schools built in Huntsville. Huntsville is growing big time. So very soon, my wife graduated from Grissom, and that's how I know all 3 of those are there. Okay. Apollos 2 through 6, and that took more than a year. Those, if they ever left the ground, they didn't go very far because they were trying to work out all the bugs. And finally, Apollo 7 was the first Apollo mission in space following the Apollo 1 launch pad. Only 11-day mission to validate the hardware. They just went around low Earth orbit, didn't get close to the moon. Okay? Apollo 8, first mission to orbit the moon. They didn't land though. Okay? Apollo 9, the first test of the lunar module in space. Apollo 10, okay? Trial rehearsal for the moon landing, but they didn't actually make it. Apollo 11, the most famous, probably. You'll recognize these names: Neil Armstrong, Mike Collins, and Buzz Aldrin. Armstrong was the one who first set foot on the moon. One small step for man, one giant leap for mankind, or something like that. Okay? Apollo 12, landing was very accurate. Did quite well. Conducted more moonwalks, really great. Okay? Anyone know about the next one? Apollo Lucky 13. What happened with that? Close. Okay. This was our first abort in deep space. Second? Yeah, we made it back, but just barely. The lunar module was used as a lifeboat to return to Earth, the crew to Earth safely. The whole spacecraft was supposed to come. They had to get into the lunar module, and that guy had to fly it back. And that had never been done. I don't think ever been practiced. They were going by the seat of their pants. And if anyone remember, there was a movie, Apollo 13, cleverly named. And Tom Hanks was the lead guy in there. Kevin Bacon was in it. I don't remember the third guy, but they were the ones who played those roles. And the very famous quote of that, Houston is the Space Flight Center, is in Houston. And when whatever happened, they got on the radio and said, "Houston, we have a problem." Okay, those lines are still used. I use them in class all the time. When we can't get something worked out. Houston, we have a problem. That's pretty famous. That's Apollo 13. Okay, it took them another several months before they tried again, and then Apollo 14, 15, 16, 17, all I think made it to the moon, took samples, did all sorts of stuff. Okay, each one of them setting new records and stuff. But we know that first one, and we know the one that blew up. Okay, didn't blow up, but they had to abort in space and fly back in a lunar module, which was not very fun, I'm sure. Okay, so those were the 12 that actually did something with the moon. Several didn't ever make it to the moon. They just tested materials. Okay. So now let's look at the composition and features of the moon, which starts at the bottom of page 424 and goes into 425. Now, go back a slide or two, and what has happened a lot of times on the moon? Craters, no atmosphere, meteors have pummeled the moon's surface. I mean, crash, crash, crash. You know, not all the time, but over the centuries and millennia and longer it's been there, it's had a lot of hits, taken a lot of hits. So therefore, the surface has been pulverized, literally. There's about 3 meters of fine gray dust on the surface. Now what does that mean? I'm about 2 meters tall, the ceiling's close to 3 meters, right? That much is just fine dust. So if they had been wearing spike heels, they would, no, they wouldn't wear spike heels. You know, now, accumulated from the micrometeor impacts, not just big meteors, small, any meteor makes its way and hits the thing. And most of that dust is small glass beads, meaning it's sort of spherical in shape, because when they hit, enormous amounts of heat, because they come in fast, enormous amounts of heat is produced, it melts the materials, and then it resolidifies. And the smaller surface it resolidifies is sphere. So that's why it's mostly glass beads. I had a professor in University of Georgia. He was my major professor when I was doing my master's, and he was from South Africa. And he always called it gloss beads. I thought, what is he saying? But gloss. And so I always think glass beads, gloss beads. Okay, now the rocks are mostly basalts. Now I don't know if that means anything to you now, but after next chapter it should. What the basalts are the rocks formed from molten lava. Okay? Now, 2 things about that. Most of the time, the center of the earth, the core of the earth, the melted part, and probably the solid part too, is mostly iron. Very high iron content. So is the moon. So the molten lava is going to be very high iron content, which means it's very dark. So you're dark, that's your Maria. That's what showed up as dark on the map that we saw. When you look at the moon, the dark areas, that's why they thought they were seas, they were molten lava. The lighter colored highland rocks were formed about 4 billion years ago. Okay? Now, 4 billion years ago. What happened about 5 billion years ago? Second? Okay, no, they weren't nearly that long. 5 billion is how long the sun's been around, right? Remember, it's about halfway through its lifetime. Its lifetime's about 10 billion years. It's been around about 5 billion years. So this means these highland rock were formed about 4 billion. Now, a billion years is a long time, but in the scope of things, that's pretty far back there too. Just a billion years after the sun was formed. Well, remember, and we haven't gotten to this yet, but they think that the moon came out of the earth, that some big collision happened that broke so that may be that these light-colored highland rock were maybe shortly after that big collision happened. Okay? The dark-colored Maria rocks range from 3.1 to 3.8 billion years. Okay? Now what does that mean? 200,000 years after these, up to 900,000 years, that's when the volcanic eruptions were happening that formed the lava rock. Okay? So this wasn't long after it. I mean, 200,000 years sounds like a long time to me. 900,000 even longer. But, 900 million. 200 million and 900 million. But, really, it's not. It was pretty close in time. So that's when it was active. Volcanically, seismically active. Okay? So, the internal structure. That's big. The 65 to 130 kilometers of outer rock. Okay? And this would be mostly that lighter colored highland rock. But the thickest is on the far side of the moon. The thinnest is on the near side of the moon, which again supports, if this broke out of the Earth, that far side would have more of the Earth's surface material on it, and this would be deeper Earth material, which wound up on the surface, which would be thinner on this side. So sure enough, there's another indicator that maybe it did come. The thickest part is on the far side of the moon. Have we ever seen the far side? No, we haven't. Those astronauts who circled the moon, yes, they've seen it, but we haven't seen it because the same side faces us all the time. So we don't see that far side. And about 900 kilometers are partly molten iron core. Okay, that's pretty interesting. Partly molten iron core. That's 900 meters. I think they mean thick, meaning it could still erupt. Okay, volcanic activity. But that the thickness of this outer rock is so great, probably it's not going to. It's only partly molten. That means it's probably, now this is just a guess on my part, back 4 billion years ago, it was a pretty hot place because volcanic activity and stuff, even through 3.1 to 3.8 billion years, a lot of seismic activity going on there, okay? Now, it's been really quiet, and we're going to get to this later. So, even though the iron core is partly molten, it's probably cooling off slowly, very slowly, but it probably not in the action of erupting any longer. So here's the history of the moon. And this is on page 425 is where it starts. And they got one thing wrong from here. We'll get that corrected in just a second. Okay, history of the moon, stage 1, the origin stage. Now, this is what we think. This is a theory. We don't know this for sure, but it seems to have been formed from material that was ejected from a collision of a large object with the Earth. Now, again, in my mind, this was way back very early in the solar system formation. Maybe the sun had just become a star from being a protostar to become a star. There was lots of junk flying around there, out there from all the explosions that came while it was a protostar. And one of those large objects hit the Earth and broke off a chunk of it, making the moon. Okay? Evidence for this is the fact that we always see the same side of the moon, so that was just a piece that flew out there and it goes around just like it did before. Okay? We're spinning, but it still faces just like it did. Other evidence is that the back side is thicker surface material than the front side. That means this came from deeper in the Earth, that came from further on the surface of the Earth, so that makes sense. So they think it came from a collision with a large object going back. And then the other thing is look at the other terrestrial planets, the ones close to the sun. How many moons does Mercury have? None. How many moons does Venus have? None. Okay? And we have one of the biggest moons relative to our size, the biggest moon relative to our size of any planet in the solar system. Sure, Jupiter has 4 bigger moons. Saturn has at least 1 bigger moon. But look, those are huge planets. Those are giant planets. We are a tiny little planet, and we have a moon almost as big as theirs are. Their biggest moons are. Okay? So that's another indicator it probably formed from us. Mars has 2 moons, but they're small moons. And what's the next thing out from Mars? What? What? No, yeah, that's the next planet. But what's right between Mars and Jupiter? The asteroid belt, okay? And I bet you Mars picked up a stray asteroid, a couple of them, that's what makes their moon. Probably nothing like the other. Now, big collision with Earth, that may lend itself to that theory that Venus had a big collision too, maybe about the same time or so, when it started spinning backwards, very slowly. Like that. All right, so there was stage 1 when it was formed. That collision, if that happened, that was one hot, miserable thing, I bet. And both the surfaces were probably molten at that time. So stage 2 is the molten surface stage. The molten surface was about, they think, 100 kilometers deep. It's pretty far down there. And they think that's about 200 million years after the collision, after its formation. Okay? The heating from the solar system, debris, impact, there were probably lots and lots and lots and lots of stuff that was impacting it that probably kept the surface with all those impacts hot enough that it was still molten. Okay? Talking a lot of energy. Stage 3. Finally, the surface cooled enough to solidify, and now the molten interior stage. Accumulated heat from radioactive decay. Remember, radiation decays at what they call half-lives. If you have radioactive material, which you would after the sun has had multiple, probably radioactive explosions once it started its fusion of hydrogen and helium, it probably sent a lot of radioactive material out there, maybe left over from the previous star when it had its big supernova that happened, and that let off radioactive materials. But anyway, the accumulated heat from that was now concentrated in the interior, so the molten interior. Now they say, and this is where I find the error here. It says it began 3.8 million years ago and ended about 3.1 million years ago. Have you seen those numbers before? With different words after them? That was when the Maria was forming 3.81 billion years to 3.8 billion years. No coincidence that the numbers are the same. It's that they got this wrong. Those should be B's there, not M's. Those are billions, not millions. Again, I think the typesetter missed that and they didn't pick up on it. Because if you look in your book, you'll see 3.8 billion years, 3.1 billion. Well, guess what was happening? Molten interior, volcanic activity. Volcanic activity, lava flows. Lava flows, basaltic rocks. Yes, it's all making sense. Those are billions, not millions. Okay? Molten interior stage. Okay? Then stage 4. And again, you see in your book, 3.1 billion years ago to present. So, when did the moon form? Well, the earliest things we know about the light color Highland rocks formed about 4 billion years ago. So it was sometime before that the collision with the Earth happened. As the collision happened, that it broke off from the Earth. Well, the sun had only been a star for about 5 billion years, so it was sometime in that first billion years that this happened, and then the solid material on the surface, and that was probably after here, that probably began in there. Then you had your seismic activity, molten interior, when you had volcanoes and earthquakes and moonquakes and things like that. That was all there. So it couldn't have been here much longer than 5 billion years ago, because that's when the sun was formed. So somewhere 4.5 billion years was stage 1 and stage 2, 200 million years after the formation. And then stage 3 was the molten interior. That was a total of 700 million years in there, but that was still 3.1 billion years ago. So for the last 3.1 billion years out of a total of less than 5. So you see, stage 4 is the longest, the coldest, the quietest. It's not doing much of anything. That happened from 3.1 billion to the present. The surface scarred by micrometeorites and other meteorites. That most of the craters were formed in the last 3.1 billion years. Before that, you had volcanic activity, so not many craters would have been forming there unless they happened to hit molten lava when it occurred. Before that, the surface was molten. It wouldn't have had any craters in it because it was a liquid, okay? And before that was origin. Okay. So that's the history of the moon. The longest, latest phase of that, not been doing much of anything. I think they still, every now and then, register a small moonquake, tremors in the moon, but nothing major. So, now we look at the Earth-Moon system, okay? And this is 16.5, okay? Now, I've said this several times already. The ratio of the moon's mass to Earth mass is still pretty small, but it's the largest ratio in the solar system. The biggest moon in the solar system around Jupiter, the ratio of its mass to Jupiter's mass is minuscule. I mean, very, very tiny. Titan to Saturn, still very, very tiny. The ratio of the moon to the Earth, probably less than, more than a tenth of something around that. You can go back to the table and see that. The diameter is a full quarter of that of the Earth. Wow! It's a quarter of this. If this is the moon, the Earth is only 4 times that in diameter. None of the others even come close to being that big, comparatively. The mass is about 1/81st of the Earth. That means the Earth is much, much denser. But of course, 4 times the mass, that's 16 times the volume, approximately. No. Or 64 times the volume. 64 times the volume, but then the Earth is much denser, especially in the center. So it's only, the Earth is 81 times more massive than but still, nowhere else. I bet you for Jupiter, it would be 1/8000th, not 1/81st, okay? And maybe even worse than that. It is large enough to affect the Earth's orbit, okay? We don't just go around the sun in a nice, smooth path, even though it's elliptical. It's not nice and smooth like that. Because we got the moon going around us, we're doing this. The moon's pulling and pushing and making us do this kind of motion, okay? So it does affect our orbit. I think this next slide shows that. If it were tiny, 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 like Mars moons or Jupiter moons or something, compared to them, then the Earth would just go on a pretty even elliptical, smooth elliptical path. But since its mass is so much bigger, then when it's over here, the moon, Earth's there. When it's down here, the Earth's here. It just keeps the Earth, the center of mass between the moon and the Earth, that's right about here. It's still within the surface of the Earth, the center of mass is. The moon is pretty small, but it's enough that makes us wobble when the moon goes around. Wobble is not the right word. we walk like a drunken sailor. I mean, we sort of do that kind of thing. Okay. So the Earth and Moon rotate about a common center of mass, meaning this is what the spin is. So the Earth spins like this, the Moon spins like this. So it seems to be going around. This isn't for all intents and purposes it is, but when it does, we are not stationary either. We're moving, much less than the Moon does. Okay? Now, what do we mean by the phases of the Moon? Well, these result from the changing relative positions of Earth, Moon, and Sun. So let's pick some time here. We said this was about spring equinox. It doesn't matter when it was. Okay? When we're here, the sun, you're going to be the sun again, you're not too hot. Okay. All right. So she's the sun, here's the Earth, and here's the Moon. When we look up and see that moon, what does the moon look like? Yeah, it's going to be close to a full moon, because the whole side of the moon that we see is going to be lit by the sun. Now, if the moon's over here, what do we see? Half moon. When the moon's over here, that's called a new moon. We don't see the moon at all, basically. We may see sort of just the shadowy side of the moon. When it's over here, half moon again. Okay? So that's what's happening. That's the phases of the moon. When it's here, it's called a crescent moon because we just see a little bit lit. Or over here, it's a crescent moon, a little bit lit. Over here, it's called, we'll get to those terms later, the gibbous moon. It's mostly lit, but not totally. So that's what the phases of the moon are. They result from the changing positions of the Earth, Sun, and Moon. The new moon is when the moon is between us and the sun. The first quarter, okay, that's not when Alabama scores a lot of points. Now, first quarter means between the new moon and the half moon, first half moon. Then the full moon is when it's on the opposite side, but the full face that we see is being lit by the sun. The last quarter, that's when they hold up the fourth note. The last quarter is when you see the second half moon, when it's decreasing in size, and those are basically the phases of the moon. In between the new moon and first quarter is the crescent. Between the last quarter and the next new moon is the crescent. And between the first quarter and full moon is the last quarter. It's what they call a gibbous moon. Now, the same side of the moon always faces the Earth, which is again indication that probably the moon broke off the Earth after some enormous solar collision. Or collision of something. So here's a picture. And by the way, we're not going to get to the lab today, obviously, but this picture is almost identical to what you're going to do in the lab. Okay? The only difference is there's two differences. There's going to be more moons in here. Okay? It's all one moon, but just different positions. The other thing, for some reason on the lab, the sun's over here shining here. But you notice the half of the Earth that's facing the sun, that's lit. Okay? That's daylight then. The half of the moon facing the sun always is a half that's lit. Okay? In our lab, everything will be reversed because there, the sun's going to be over there. Okay? So you're going to have something like this, and you're going to fill in the half of this moon and sun. No, Earth is already filled in. That is lit, and the half that's dark. Okay? So when we're here on the Earth looking at this moon, we don't see anything lit. Full moon. Lit, I mean a new moon. Anything over here, we barely see a crescent on either side of this. The crescent gets bigger as you move, of course you move it this way and this way. The closer you get to away from the new moon, the crescent's bigger. When you get there, we call it a half moon. This is the first quarter, last quarter. But then past this is half moon. After this, the lit side gets bigger and bigger till right here you see the whole moon is lit. That's the full moon. And then it starts reducing until you get a half moon, reducing until you get no moon, new moon. Okay? Now, always, whether it's a little crescent or a big chunk of the moon, the part that's lit is always the part toward the sun. Always. So if you see, and you'll see these crescents right around sunset or sunrise, one or the other. And when you see that, you know where the sun is. It's the middle part of that, the sun is that direction. Got to be. Okay? Same thing is true when it's mostly lit. The side that's fully lit, that's the part toward the sun. Always the most illuminated is toward the sun. That sort of makes sense. Okay? Now, let's talk a little bit of eclipses. Okay? Now, it sounds like the term ecliptic, and there's a reason for that. The moon's orbit is about 5 degrees out of line with the Earth's orbit. Meaning if the Earth is going around the sun like this, the moon's up here 5 degrees out from what this is. So most of the time, the moon is nowhere close to the shadow of the Earth at all. But every now and then, it does pass behind the Earth's shadow. Now that's going to happen closest to a full moon. In fact, almost always on a full moon. I believe it is always on a full moon. Most of the time, the full moons will be somewhere where the Earth does not, the shadow of the Earth does not interfere at all. But when you do see an eclipse, a lunar eclipse, that means you've got a full moon. The moon's on the opposite side of the Earth, but it's in the shadow of the Earth. And we'll get to that next thing later. Okay, in fact, let's do that now. These are our lunar eclipses. No, we're going to talk about solar too, so let me mention solar. When we're here, the Earth's here, the sun's over here, right? When the moon is here, that's when we get a solar eclipse. And those are always new moons, because the moon's between us and the sun. The half away from us is what's lit, the half toward us is dark. Now, most of the time, those new moons are going to be not in the direction of the sun at all. But when they are, that's when we get a solar eclipse. Was anyone around was it October? Yeah, when the big solar eclipse. We didn't see all of it. We had a partial eclipse here. If you drove up to Nashville, I think around Nashville somewhere, you could see a full solar eclipse. And I know some people who did that. You go up and see it. Now, that's what they mean by the proper alignment of the Earth, Moon, and Sun are needed. Only time you'll have a lunar eclipse is on new moons, and full moons. Most full moons will not ever have a lunar eclipse, but when they do happen, it has to be a full moon, and the moon passes in the Earth's shadow. Only time you get a solar eclipse, it's a new moon passing in the, making its shadow hit the Earth. And that's very, very rare. Most new moons, nowhere close to that. And here's why. Now they could have made this picture far, far, far better. Okay? This is not bad. The moon casts a shadow because the sun's way, way out there, and the moon's a very little thing, so it casts a very thin shadow. And that's as far as the shadow goes because the sun's rays merge beyond that. So to get a lunar eclipse, a solar eclipse, then the moon has to be directly in line with the sun and the Earth. And even if it's directly in line, the shadow has to touch a part of the Earth. And by that time, the shadow is very, very small. So most of the time, it's going to be a tiny little area that is going to happen. So this is the position. If this is the plane of the Earth's orbit, and this is the plane of the moon's orbit, and you know those are 5 degrees different from each other, most of the time the moon's not going to be anywhere close to doing it. But if the moon happens to be passing right here, when it's either a new moon or a full moon, the sun's out here, then you're going to have potential for an eclipse. Okay, now picture this. When it's here, that shadow just barely reaches the Earth. That little bit of shadow that touches the Earth, that's where the only place you'll see a solar eclipse. Very small. Okay? Now, sometimes it doesn't quite reach, and we'll talk about that in a minute too. When it's back here, here's how this picture should have been better. They should have shown a picture of the Earth shadow. Okay? And the Earth shadow would be a much bigger cone, but it is a cone that ends down here. It's much easier for the moon to pass into that big shadow than it is for this little shadow of the moon to strike the surface of the Earth. See what the difference is? So therefore, you'll much more regularly see lunar eclipses than you will solar eclipses, because the Earth shadow is much bigger than the moon shadow. So it's only going to be little bitty times. Okay. I'm afraid we're out of time. So we won't be able to finish this. Okay. So basically we'll pick up then okay. We may just start over with eclipses because we've got to repeat some of that. Okay. Now this means two things. Number one, we're just within a few pages of finishing the chapter. But we did not finish the chapter. So that means on Thursday, we will finish this chapter in very short time, and then we'll go on to chapter 17, which is a whole new story, okay? Now, the next thing it means is we'll have this lab the last 2 hours of Thursday's class, the lunar lab, okay? But we will not have the chapter 16 test because we didn't finish the chapter today. So that means the chapter 16 test will be next Tuesday, the last 30 minutes. Even though we'll be well into chapter 17, possibly even finished it, I doubt it, but well into chapter 17. So that's where we'll end today. Are there any questions? Bless you. Or was that a question? No, never mind. Okay. So if there are no questions, I want to go on and shut